So if you follow the channel, you'll know that we've acquired a bunch of 14-inch Pye monitors, albeit in rather shabby and sorry condition. Hopefully we'll be able to make a few good ones out of the collection here. These date from the late 1960s, but for the last 20 or so years they've been stored in pretty damp and latterly wet conditions, so it's really taken a toll on the fabric of these monitors. All the rust you can see there is on the mild steel parts, and there's corrosion on the aluminium as well. Fortunately, some of it is surfaced rust, and that can be brought back. Even those knobs there on the screen protector will clean up quite well. Rust here is a little bit more tricky, but we do have some spare panels. Biggest problem is the fact that water has dripped into the gap between the steel and the aluminium, and it started to react with the aluminium and it's starting to blow out there. Some are worse than others, so hopefully we can mix and match to get a good set. Electronics has fared not too badly. Electrolytic capacitors obviously have oozed and leaked, some more than others, but we'll see what we can do with the electronics a bit later on in this video. So it's been about 10 days since we've had this monitor, and 2 or 3 times I've soaked the switches, which were jammed solid, rusted solid, with a mixture of WD-40 to try and free them up, and also some Servicol 40. Both claim to do roughly the same job, which is to repel moisture, free stuck parts, and leave behind a protective coating on the switches. So as you can see, they now move, much to my relief and surprise. They move reasonably smoothly. 3 of them are termination switches for the inputs, and we can check that the switches are actually working electrically by just measuring the resistance across the input connectors. And hopefully you can see that that is open circuit, but if I move the switch, we see our 75 ohm termination, and the same is true for the other one, so that's kind of a relief. So I think the next job is to hoover out some of the insides. I've done some cleaning already, just to make it a little less unpleasant. There's a lot of corrosion inside here on the EHT box, but I'm going to take that out and look at that separately. Also got a big pile of dirt to tidy up there, so at this point I think we'll bring the hoover into play. Well, on the basis it's never a proper job until you've either cut your finger or broken a tool. I've just had to regrind the end of my screwdriver, as this screw here managed to shear the end off it. I've managed to undo that, and we're going to have a look under here just to gain more access to the components below. So what I want to do is I want to have a look at, in particular, the state of the electrolytic capacitors. It is quite difficult to tell on some of them whether they're going to be any good or not, but bearing in mind the history of this monitor, and we know that it's lain in damp conditions for more than 20 years, I think we're going to have to treat all of these as potential replacements. Just looking at them, I can see corrosion emanating from the ends of the capacitors, and I've had trouble with these in particular in the past, with the wires just corroding off and failing. So I know we end up with a bit of a triggers broom situation with these restorations, whereas we like to keep as much original as possible. if you think about during the service life of these pieces of equipment, they would have components routinely replaced when they failed. So I don't think we can be too precious about changing things that are clearly going to be causing problems, even if they work at all, like that. But at this point I'm still in the visual inspection phase of the restoration. But I'm going to make a note of all the component values and make sure we've got some suitable spares for the next phase. And this is the bar to which the circuit board is screwed. This screw at the end was missing, which is why the whole thing was flopping around. That's cleaned up quite well just by rubbing it with some tissue paper, so that can go back in pretty much as is. And it's a similar horror story on the power supply and line scan board. This capacitor here is across the main 11 volt power supply, and you can see that it's oozing its electrolyte out there. Not quite so many electrolytic capacitors on this side, but these two are quite interesting. We'll have to measure those, I think, to see what they're like. These are in the line output stage of the monitor, so these are kind of vital to the geometry of the scan. If necessary, we could replace these components with a more modern one like that, which would probably fit in quite reasonably well, but we'll see how we go first. It's interesting to note this transistor here. It's date stamped year 81, week 8. So we know that this monitor has had a service life that extended into the 1980s. Let's have a look and see what lies below this heatsink. Get the last screw out. It should just hinge out of the way. Oh dear, yes, we can see we've got another leaking electrolytic that absolutely has to be replaced. These TCC branded ones all seem to have suffered the same fate. My guess is that they're not as hermetically sealed as as some of the other brands. Better news over on this side is that the system select switch, the 405, 625 and 525 lines switch, which was totally solid, has now cleaned up with some lubricant and switch cleaner and is now operating satisfactorily. It's worth pointing out that the overcurrent circuit breaker, which is all gummed up and corroded and stuck fast, that now operates cleanly. Now, of course, it's worth bearing in mind that these monitors were professional pieces of equipment in their time, and as such were designed to be repaired, and repaired easily. For that reason, each of the functional blocks of the monitor can be powered separately and serviced separately, and that's exactly what we're going to be doing. For these particular monitors, there's a logical sequence in which the boards can be examined and repaired. That is to say, we'll first fix the low voltage power supply, then we'll move on to the video input and amplifier. That logically leads us on to the sync separators, which in turn drive the field and line scan boards. And finally, we'll look at the high voltage power supplies that drive the tube. It's worth pointing out also that we can run all of these boards on a bench power supply. That makes it a lot safer while we're investigating what is likely to be multiple faults. So, without a suitable new cliche in mind, let's get started. And it looks like that during previous repairs to this monitor, these have been desoldered, so I'm quite confident this is a valid form of proceeding with repairs on this monitor. So I'm going to take out C403, which is leaking quite badly. I've desoldered it. I'm just going to wriggle it out of these and you can see how horrid the end of that capacitor looks. I think we're just going to fit this one in position, give it a quick clean up. There are only 3 electrolytic capacitors in the regulator circuit, so I'm going to change them all because at this stage I think we need some confidence that we've got good components in place, and then we can just test it. Right, so I've soldered in the new component. It is a radial capacitor, so I could have mounted it directly into the holes, but I thought I will mount it in the manner of the original, even though it's a much smaller component, and tie it down with the existing lacing straps here, because it's still a fairly large component and there could be vibration in the vehicle and things like that it's going to be fitted in, so eventually that will mechanically fail. So that's the reason that the big components are mechanically tied down in these monitors. It's to stop principally vibration failures. The other factor is that it didn't really fit very well because of that wire link there. It wouldn't sit flush to the board. So I've got my bench power supply connected to the two smoothing capacitors here. Nothing else in the monitor is connected to these capacitors. The circuit breaker is open, so there's literally nothing else other than these capacitors. The bench supply I've set to a very conservative, just 12 volts with a current limit of 0.7 amps. And I'm just going to turn it on and we'll have a look at how much leakage current there is on these components. And you can see that the current settles to a value of around about 8 milliamps, showing that there is a fair amount of leakage on this, these pair of capacitors. Bearing in mind they are over 50 years old, maybe that's not surprising. I'm going to have a little think about whether this is an acceptable value. Now, if you remember, I was a bit concerned about the current leakage on these capacitors after I'd reformed these electrolytics. As you can see on the power supply, we're still drawing about 7 milliamps, and I put that down to leakage. After all, the circuit breaker's out. In theory, there's nothing else connected to these capacitors, but that was where I was wrong, and I've really sort of gotcha'd myself. And by looking at the circuit diagram and also inspecting visually, I should have spotted these tiny little wires connected here, which tap off these capacitors before entrance to the circuit breaker here. And a quick look at the diagram shows that these are to do with the video input switching relays. For some reason they've taken these feeds directly from the main capacitors before any protection. Can't really figure out a good reason for that, but anyway, that's how it's done. So our 7 milliamps is actually coming from the relays here. So if I select remote by putting to that position, miraculously both relays open, and because there's no remote control plug in situ, and there's no video relay operating, and there's no leakage current now. So, well, certainly less than 1 milliamp. So pretty happy that those capacitors are actually good. The final check, of course, will be to apply mains power, so we've got proper ripple going into those capacitors, and we'll have a look at on the oscilloscope to be sure. But first indications are that they reformed satisfactorily, and there's not really any bad mechanical or leaky electrolyte oozing out of them, so probably they're okay. So now with 16 volts on the power supply, we've got a leakage around about 11 milliamps. So now is the moment of truth, and we're going to see whether the 11 volt power supply is actually working. If I hit the circuit breaker on the monitor, that will supply the input of the regulator, and we're going to see what happens. Well, well, well. We've got a working 11 volt power supply. Okay, there's no load on the power supply, but it appears to be giving out the rated voltage. So the next thing to do is to introduce a load to the circuit. This is an 8 ohm dummy load inside here. I've increased the capacity of the power supply to 2 amps. So a bit of maths, 8 ohms, around about 12 volts. We're looking for about 1.5 amps, aren't we, if this is working. The important thing to do is to have a look at the voltage to see if that is being regulated. So I'll just put the ground on and we'll see. So the power supply is showing now just under 1.5 amps, as I would expect, and to our relief the regulator is still producing minus 11 and a bit volts, so that's hardly changes between a reasonable load and no load. That's pretty good. So that's passed that test, so I'm fairly confident that we've got a working minus 11 volt power supply. Well, there's some progress. So I'll jump straight in, and we've got the video sync and vertical scan board out here. We've got our staircase going in here, got some external sinks going in here which we're not using at the moment, and I'm scoping on the emitter of TR103, and good news is we've got a signal, and I can control that signal with the contrast control, so that proves that a fair good bit of the circuit's absolutely fine. The resistor that's given problem in previous monitors, that's good. The control is nice and smooth as well, so that's responded to the switch cleaner, so I'm pleased about that. We can now also look and see if we've got any sync separation going on, and we'll jump straight to test point 4, which is the horizontal sync, which is down here. Oops. And looks just like the picture in the manual. And if I switch to external sinks, I get nothing at the moment until I plug the cable in, and yeah, we've got the same signal there, so that proves the external sync input is nice and healthy as well. We'll now look at the vertical trigger. Now looking at test point 6, which is the vertical sync output. On the scope we've got a nice sharp vertical sync lining up with the field sync of the input waveform. So there we have the vertical sync pulse here lining up nicely with the input waveform. It's quite difficult to see perhaps on camera that, but there's a nice sharp pulse there. What I do notice though, that if I switch to external syncs, that pulse goes, so there is a problem with the external sync input despite it showing horizontal syncs correctly, so I need to have a quick backtrack and have a quick look at that perhaps. Well, this little fellow is the input coupling capacitor for the external sinks, and it looks a little bit unhappy, its label's falling off, it's a bit corroded at the other side. So what I'm going to do is I'm just going to temporarily short across it with this 68 microfarad bipolar electrolytic and see if that makes any difference to the waveform. So there's our slightly horrid waveform, distorted sync tips. If I connect the replacement capacitor across the suspect one, there we go, some nice clean sync pulses. So I think that's positive indication that capacitor is no good. Right, so we've got field drive output working around about 30 volts peak to peak, which feels about right, ballpark. The shape looks about right. We can look at the return side of the field coils as well, for which there is a picture in the manual. So it's going to be much lower. Again, that looks about right. It's about quarter of a volt or so, which corresponds to about 0.3 in the manual, so I think that's about right, ballpark, and the shape looks about right. So as a first pass, I think we've got a working field scan stage. I've not done any work at all on this. We'll have to see what the picture looks like when we actually get it on the screen, but as a first attempt, I think that's pretty successful. Now moving over to the horizontal scan board, I've just got this powered off the 11 volt power supply. No other boards are powered, so it's just this board, and it's obviously free running because it's got no locking signal from the other boards. Just checking the waveforms are as per the diagram, and this is the waveform at the emitter of TR303, and that's nice and in spec. And if we look at the horizontal output itself, which is going to be much higher voltage, there it is, and that looks pretty good. That's around about 220 volts as per the diagram. So we've got the basic functionality of the horizontal stage checked out. I mean, there are things that could be bad about it. The linearity could be bad. It may not lock to the sync input, so we should check that. There are some slightly suspicious looking capacitors which could probably do with changing, but I think the basic functionality is there. So I think next step is to reassemble the monitor with the EHT power supply and give it a go. Well, it's been a few weeks since I've worked on the monitors, as it's been so cold out here in the shed, but we have got some positive news. I won't bore you with fault finding these power supplies again, because we've dealt with that in previous videos, but suffice to say that one of the rectifier valves was short circuit. I pulled a spare valve out of the next monitor in the restoration queue. That was also dead, but the other valve in that power supply was good. So we've got one good power supply. Relief to see that these doorknob type capacitors are actually okay in this particular power supply. So we'll just turn it on the power supply, and within 5 or 6 seconds or so the EHT will build up nicely, as we can see up here, to around about 14,500 volts, which is good enough, and we've got just under 100 volts on the 100 volt line, so it's a little bit low. I've changed a few other components which have made no difference. I'll put them back, so I'm just going to figure that this is a nominal figure, and it's close enough. Current consumption is not excessive, so again that shows that there shouldn't be too much leakage going on. So I think we'll call that one a fix on this power supply, and we can move on now to look at some more work on the video board. Right, so the next stage is I've plugged the mains in. I've got a scope across the minus 11 volts, and we're going to try powering the power supply from the AC mains and see what happens. Nothing, that's interesting. What? So the reason why we haven't got any power is that these two rectifier diodes are completely open circuit. I don't have any spares for these, so the alternatives are to replace them with a more modern component, or to swap them with one of the some donors from one of the other monitors. Okay, so I've bodged in a couple of modern power rectifier diodes, and we'll see how that behaves now. Right, so this is the moment of truth time. Let's turn it on and see what happens. Well, we've got 11 volts on the power supply. Something unpleasant going on inside, and not a lot else really. Time to switch off and investigate. Don't know if you can see that, probably not, but there is flush over inside the tube. So we've got a bad tube, I think. What a nightmare. That's a real shame. That That is a real shame, because everything else was looking in favour with this monitor. Oh well, some you win and some you lose, I guess. If I turn the contrast up, we have got an image on the screen.